Welcome back, everyone, to this explainer on advanced engineering mathematics. Look, today we're taking the abstract, highly theoretical world of first-order differential equations and we're turning it into concrete, usable engineering data. We are building that absolutely crucial bridge between the geometry of these equations and the actual numerical solutions you will use every single day in the field. I mean, whether you're analyzing a ridiculously complex circuit or mapping out an electromagnetic field, really understanding what your equations mean, both visually and algorithmically, is exactly what separates a good engineer from a truly great one. So let's just dive right in. Okay, here is our roadmap for today's session. First up, the geometric meaning and slope. 2, direction fields, which is our graphic method. 3, Euler's method, diving into the numeric approach. And finally, number 4, a step-by-step Euler computation. Right, let's hit section 1, geometric meaning and slope. So to really grasp these advanced numerical methods, we actually have to start with a fundamental geometric truth. You probably remember this from basic calculus. When we write a first-order differential equation as y prime equals f of x, y, that equation is handing us a very direct rule. It tells us that the derivative, y prime, is literally the slope of the function y at any given point. Because of that, the solution curve passing through any specific point, let's call it x0, y0, absolutely must have a tangent slope that is exactly equal to the value of f at that point. You can kind of think of the function f as a GPS. It gives us the exact direction, or the slope, for every single point on our coordinate plane. Moving right along to section 2, direction fields and the graphic method. Okay, so think about this for a second. What happens if we take all those calculated slopes and just plot them across the entire plane, instead of looking at one single point? Well, you get a direction field, sometimes called a slope field. Take the differential equation y prime equals y plus x. If we plot this, we get all these short, tiny line segments scattered everywhere. We call those lineal elements. Imagine dropping a tiny drop of liquid right at a starting point, say 0, 1. It would flow upwards, perfectly tracing the tangent directions laid out by those little lines. Actually, for those of you specializing in electrical engineering, this is practically identical to visualizing lines of force in an electric field. This slope field is incredibly powerful because it reveals the typical properties of the entire solution family in just a single glance, even when we don't actually have an analytical solution formula. Now, if you ever need to do this manually, without a computer algebra system doing the heavy lifting, there's a really logical, procedural way to do it. First, you draw your level curves, which is where the value of f of xy is constant. We call these isoclines, which translates to curves of equal inclination. Because the derivative is exactly the same everywhere on that curve, the slope is the same, right? Then step 2, you draw parallel lineal elements, those tiny line segments we just talked about, along each of those isoclines. And finally, you just manually sketch approximation curves that follow the flow of those lines. It's honestly like fitting a curve to the wind in a wind tunnel. It's a fantastic, hands-on way to understand the true character of whatever equation you're dealing with. Which brings us to section 3, Euler's method, a numeric approach. Now, visual estimations are great, but let's be real. In engineering, we usually need hardcore mathematical precision. So how do we actually compute these curves numerically? Let's break down the geometry. Consider an initial point, x0, y0. The true exact solution curve bends naturally from there. But here's the catch. We don't actually know the formula for that true curve. All we know is the slope, the tangent, right at our starting point. Enter Euler's method. What we do is step forward along the x-axis by a very small fixed amount. We call this step size h. That gets us to x1. Now, on the y-axis, we move up by an amount equal to the slope multiplied by that horizontal distance. Basically, h times f of x0, y0. Boom, that gives us our new point, y1. But wait, think about what we just did. Because we traveled along a perfectly straight tangent line, we totally ignored the natural continuous bending of the true solution. And that right there creates a gap between our calculated point and the true curve. That gap is our error at y1. The algebraic translation of that whole geometric triangle we just walked through is the general Euler formula. Yn equals yn minus 1 plus h times f of xn minus 1 yn minus 1. To put it simply, your new value is just your old value plus the step size multiplied by the slope at that old point. It's a recursive formula, and it is absolutely crucial that you memorize this algorithmic logic. When you have a computer building a solution curve numerically, it isn't doing magic. It's literally just running this exact, simple, iterative calculation thousands or even millions of times per second. All right, section 4, step-by-step Euler computation. Let's actually put this algorithm to work and see how the numerical data gets generated in real time. We're going to solve y prime equals y plus x, and we'll use a step size of h equals 0.2. So, starting at x equals 0, we advance by 0.2 with every single step. Applying our recursive formula, we calculate our new y values. Notice what happens at step 5, where x is 1.0. Our calculated y is 0.488. But hold on, let's look at the true analytic solution for this specific problem, which happens to be y equals e to the power of x minus 1. The actual true y value is 0.718, but our calculated value? Only 0.488. That leaves us with a pretty significant error gap of 0.230. If you track this conceptually, as we progress, our plotted points just fall further and further below the true solution curve. Why? Well, the true curve is constantly bending upwards, but Euler's method forces us to keep drawing these rigid, straight tangent lines, so we are constantly falling behind the actual curve. And that leads us to a massive, highly critical question for any real-world engineering application. We just watched the error grow with every single step. So, what exactly happens to our accuracy, and more importantly, our overall computational load, if we decide to drastically shrink that step size h? Like, what if we drop it from 0.2 all the way down to 0.0001? Well, as you probably guessed, decreasing h shortens those straight tangent lines. That allows us to hug the true curve much, much more tightly, and for sure, it significantly reduces our error. But, and this is a big but, this introduces the ultimate classic engineering trade-off. A drastically smaller step size means your system has to take thousands, maybe even millions of extra calculation steps just to reach your target point. That results in a massive, often completely impractical computational load. We simply can't rely on making the steps infinitely smaller to save us. And frankly, this is exactly why our source material later dives into much more sophisticated numerical algorithms, like the Runge-Kutta method in section 21.1, which managed to achieve way higher accuracy without that crippling computational cost. Always keep that trade-off in the back of your mind when you're designing your own algorithms. So here's a thought to leave you with. At what point does the pursuit of absolute mathematical perfection actually become an engineering failure? Think about that. That wraps up today's explainer. Thanks for joining.
Hey everyone, and welcome to today's explainer. I am absolutely thrilled to step in as your guest lecturer today for your Advanced Engineering Mathematics course. We're going to be tackling a massive topic, bridging the gap between the beautiful, abstract, continuous systems you learned about in calculus and the nitty-gritty, discrete approximations you're actually going to be programming out in the real world. Basically, we're taking theoretical math and turning it into computational reality.
Here is our roadmap for today's session. We'll start with the analytical barrier, move into geometric mapping, cover the transition to discrete math, talk about executing the loop, managing error, and finally, wrap it up with some real-world modeling.
All right, let's jump right into part 1, the analytical engineering barrier.
You know, as engineers, we hit a pretty harsh reality wall early in our careers. Those exact, continuous analytical formulas we spend years solving in school, yeah, they rarely exist for the complex ordinary differential equations, or ODEs, we face in industrial projects. Sometimes the math is just way too complicated, or a neat formula literally doesn't exist. So we have to pivot. We rely on the rest of our toolkit, specifically graphical methods that give us a visual map of how a system behaves, and numerical methods to generate discrete, approximate data points. That numerical approach is an absolute game changer because modern computers can crunch those numbers, no matter how nasty the equation is.
Moving right along to Section 2, Geometric Mapping of ODEs.
Before we ever write a single line of simulation code, we need intuition. Think about what a first-order ODE actually is. It is fundamentally a geometric rulebook. It tells you that if a solution curve passes through a very specific spatial coordinate, its slope at that exact point absolutely must equal the function evaluated right there. So solving an ODE isn't just about algebra. It's about finding paths that perfectly align with these predetermined slopes.
And what happens when you take that geometric rule and systematically apply it across a whole grid of points? Boom, you get a macroscopic view. By calculating these little lineal segments everywhere, you generate a direction field. What is so wild about this is that without solving the ODE analytically at all, you instantly get a clear picture of the overall current or flow of the system. Any starting condition you drop into this field is just going to be swept right along that flow.
Now, say you're doing this by hand. You can actually deconstruct these fields using something called isoclines. If you set the function equal to a constant value, you define a curve where every single slope element has the exact same inclination. It's like finding the hidden skeleton of your vector field.
For those of us in electrical engineering, analyzing this kind of visual map is exactly how we evaluate the global stability of complex power grids without having to crunch every single voltage state.
Okay, let's get into Section 3, the transition to discrete.
While mapping things visually is great for the big picture, a computer can't process a smooth, continuous drawing. To write a numeric simulation, we literally have to chop up physical space. We do this by defining a step size, which we call h. This is the fundamental sampling rate of our digital world. Instead of infinite, smooth curves, we are forcing the computer to evaluate things at strictly equidistant points along the x-axis.
So how do we make that digital jump? It's all about the Euler step. We take our known starting point, grab the instantaneous tangent slope from our direction field, and we just ride that straight line forward for our specific step distance, h. We're taking a dynamic, curving reality and forcefully assuming the slope stays perfectly constant for that tiny, rigid distance.
Let's put this into action with Section 4, executing Euler's algorithmic loop. This right here is what I like to call the MATLAB mindset. We are entirely replacing complex, continuous calculus with a simple, four-step, repetitive arithmetic loop. Step 1, input your previous state. Step 2, compute the slope at that spot. Step 3, multiply that slope by your step size h. Step 4, output your new state. It is repetitive, it is simple, and it is absolutely perfect for programming.
When you run this algorithm, say with a step size of 0.2, you continually feed the output of one step right back in as the raw input for the next. So you compute the point at x equals 0.2, plug it back into the loop to get a fresh slope, and take another step to x equals 0.4. Your computer is literally walking point by point, tracing a discrete, stepped trajectory straight across the continuous direction field.
But of course, there's a catch. Section 5, managing error and trade-offs. When you're out there building these simulations, you have to remember one fundamental, inescapable truth. Numerical error is inevitable. Think about it. We are artificially freezing a physical property that is constantly changing, treating it like a straight, static line. Real, continuous systems bend and curve. They will inevitably bend right away from that straight tangent line we drew. And that gap, that's your mathematical error.
And it doesn't just happen once. It gets worse. As you loop from step 1 to step 5, that error compounds. Every single time we assume that trajectory is linear over the distance h, our approximation drifts a little further away from the true continuous reality. The mistakes stack up.
So you might be thinking, well, just make the step size incredibly tiny. And you're right. Shrinking h means the straight line doesn't travel as far before recalibrating, which massively boosts accuracy. But here is the classic engineering trade-off. A smaller step size means way more computations. You are trading mathematical error for computational load. Knowing how to balance the need for precision against the harsh reality of processing limits, that's what makes you a good engineer.
Finally, let's bring it all together in Section 6, Real-World Complex System Modeling. Let's look at a classic, real-world mechanical problem from the course materials, the falling parachutist. Using Newton's second law, we're modeling a falling body. But wait, we have to account for air resistance, and in this model, it's proportional to the square of the velocity. This creates a highly complex, nonlinear system where finding an exact analytical solution is an absolute nightmare. This is exactly why we spent today building our numeric and graphic toolkit. Using our methods, we can visually map this system to find the limiting velocity, where the system reaches global stability and the slope flattens out. But here's a question for you to chew on. How would altering the physical rules shift that stability? What if the parachute dynamics meant air resistance was only proportional to standard velocity rather than velocity squared? Modeling that exact kind of shift using discrete algorithms is what you'll be doing in the field. To quickly recap what we've covered, we've learned how to turn the continuous into the discrete. We start with the rule, the core ODE equation. We transition to the map, using direction fields to see the macroscopic flow. And finally, we fire up the engine, using Euler's method to forcefully compute discrete steps when exact calculus just won't cut it.
I want to leave you with a thought as you log off and go write your first algorithmic simulation. As engineers, we aggressively discretize the entire physical world just so we can program it. But as you set your step size, ask yourself, what intricate, beautiful realities of the continuous physical world are we permanently losing in the gaps between our digital steps? It's something to think about. Thanks so much for joining me today, and best of luck with your simulations.